Now, first point, these are the two most efficient packings in solids. Two most efficient packings in solids. Second point is they both have a coordination number of 12. Means each atom is in contact with 12 other atoms in three-dimensional packing. So each atom is in direct contact with 12 other atoms. Now first we will discuss about the hexagonal close packing. Hexagonal close packing. Three-dimensional hexagonal close packing. It is HCP. Now in this case, this is called the layer A and they are forming a hexagonal structure. So in the layer A, each atom is in contact with 6 other atoms and forming a hexagonal layer, and the atoms of the second layer are placed in such a way to cover up these trigonal planar voids. This is called trigonal planar void. So we have placed the second layer in such a way to cover up this triangular planar void. But when we try to cover up the triangular planar void, some empty space is still left. And in this case, hexagonal close packing, every third layer has the same arrangement as the first layer. So this is the first point. Every third layer has the same arrangement as the first layer. So this pattern is repeating itself infinitely and gives a hexagonal close packing. So we are representing the layer, one layer by A, second layer by B. So AB pattern is repeating itself and this results in hexagonal close packing. Now this hexagonal close packing can be represented like in the form of a hexagonal prism. Now look at the diagram again. Now this atom Y is in contact with 6 other atoms in the same layer, 1, 2, 3, 4, 5 and 6, and also in contact with 3 red color atoms in the layer above, that is 1, 2, 3, it's the red color atoms, and also in contact with 3 red color atoms in the layer below. So in hexagonal close packing, each atom has a coordination number of 12, and the breakup is that 6 in the same layer, 3 above and 3 below. So 3 plus 6 plus 3, so total 12. So each atom is in contact with 12 other atoms, 6 in the same layer, 3 in the layer above and 3 in the layer below. And we can also show this hexagonal prism like this. So if you see in the layer A, this atom is in contact with 6 other atoms, this atom is in contact with 6 other atoms, and also in contact with 3 atoms, red color atoms in the layer above and in the layer below. But if you look at the diagram, there are 2 types of voids still left. Now look at this void, this is called tetrahedral void. So if any atom comes and occupies this void, this empty space, that atom will be in contact with 3 black color atoms and 1 red color atom above it. So it forms a tetrahedral void. So this is tetrahedral. So any atom occupying the void is in contact with 3 black color atoms and 1 red color atom above. So that is called tetrahedral void. Coordination number is 4. And this void, if any atom comes and occupies this void, that is called octahedral void. So that atom will be in contact with 3 black color atoms and 3 red color atoms. So total 6 atoms are in direct contact with the atom occupying the void. And we use the term octahedral because it is forming 8 triangular faces. So we have shown one triangular face. This is a triangular face, A, B and C. So this is one triangular face. So there are 4 triangular faces above the plane and 4 triangular faces below the plane. Total 8 triangular faces are there. That's why the name is given octahedral. In tetrahedral, we have 4 triangular faces like this: A, B, and C. This is one of the triangular face. There are 4 such triangular faces present in this tetrahedral. Now in hexagonal close packing, the packing efficiency is 0.74. It means nearly 3/4 of the volume is occupied and 1/4 of volume is present in the form of an empty space. Now examples of solids having hexagonal close packing are magnesium, cadmium. So these are 2 examples of solids having a hexagonal close packing. Now second type of most efficient 3-dimensional packing is the cubic close packing. This is also called face-centered cubic packing. Face-centered cubic packing. Now the first point is that in cubic close packing, a packing pattern is ABC, ABC, and so on. It means every 4th layer has the same arrangement as the first layer. Every 4th layer has same arrangement of atoms as the first layer. So this is the first point. And the second point is that the packing efficiency is equal to 0.74. Now this we can calculate also. In face-centered cubic, there are 4 atoms present per unit cell. 4 atoms present per unit cell. Atoms are in touch with each other along the phase diagonal. And we have already proved that phase diagonal length is 4r is equal to root 2a, and the packing efficiency is now equals to 4 into volume of one atom, 4 by 3 pi r cube upon the volume of the unit cell, and this is equal to 4 into 4 by 3 pi r cube upon 64 r cube upon 2 root 2, and this is equal to root 2 pi by 6, and this is equal to 0.74. And the examples of solids having this type of packing are copper, silver, gold. So these are 3 examples of solids having a face-centered cubic packing. And in face-centered cubic packing or cubic close packing, the coordination number of each atom is also 12. Of each atom is equal to 12, and this is the breakup: 3 plus 6 plus 3. So both these types of packing, the coordination number is 12, packing efficiency is 74%. The only difference comes in the placement of layers. In face-centered cubic, we have ABC, ABC, ABC type. In hexagonal close packing, we have AB, AB type. So this is about the 3-dimensional hexagonal close packing and the cubic close packing in solids.